visible. Am I audible though? I guess I am because
Yeah, it's visible.
okay, cool. So I'll draw a diagram, and it's hard to draw diagrams here. So if at any point the diagram just goes terrible and it's not anything is not visible, I'll switch to GeoGebra. Reason I have it opened. I'm said okay, fine. I won't comment about difficulty about this problem. So I'll do a diagram. Yeah, the circle is stupid. And then you have point P. And point Q. And then there exists a point such that PD is PP. PD meets circumcircle. So we want to prove QB is QR. So like take some time trying the problem, and even if you don't get the full solution, just say any idea that you get. Because it's like not so easy to do it in 5 minutes. But yeah, sure, it's fine.
Why is B on top right now?
Oh, just because it's B centered, right? Because like P and Q are in AC, so it's B centered. So draw B on top. It's easier to see.
Right, makes sense.
I first said it on B on the right, and it took me surprisingly a lot more time.
Yeah. Okay, like AB is tangent to circle BQC.
Yes. Okay. So I'll write the power of point thingy.
Is DRQC cyclic? That is a claim, like.
Yes, that is correct. Basically, that's just familiar triangle. Like you get that this angle is C and this angle is A, so this angle is B. And then angle ARC is angle ABC, which is also B.
Right.
Yeah, we do a DQCR. Oops. DQCR is cyclic. It does not work with screen sharing. Correct. What else do we have?
Oh, PB is tangent to ABC.
Yeah, I was surprised you saw AB tangent to BC first in that.
Yeah.
Yeah, so we also have that PB squared is equal to PA times AC. Oh, zero. CA times BC. Any ideas? Any like okay, how would we prove QB is QR?
Angle chasing?
Yes. So you want to prove angle QBR is QRP. You know this angle, right? This angle is B minus C. And you also know this angle. This angle is C. So basically just label this angle Y and say this angle X. We want to prove X plus B minus C is equal to Y plus C. We want this. Now how do we get this?
Like, can you join DC?
Yes, sure. So yeah, this angle is Y.
Yeah, and it's like,
This is X.
yeah,
We want to prove this. How do we do it? Also PBA, we have PBA is equal to C. So if this angle is C,
I
PDC.
think he means PDB, right? PDB should be to C.
Yeah. Yeah, that's correct. This angle is 2C. That is absolutely correct. Now, what else do we have? Like, how do we get like we basically want X minus Y to be nice.
Yeah, that's what I was
So how do you get X minus Y? Like it's in like it won't have to focus on triangle ADC, but that will give us X plus Y. But like we want X minus Y. How do we do that? Okay, so have we used PD equal to B?
If we extend,
Yeah, go ahead.
if we extend BQ to meet the circle at T,
Uh-huh.
Then AC bisects angle BCT.
OT. AC bisects angle
BCT.
BCT. I see, that is correct. So you have AB is
Yeah, but
80.
like I don't see how to use this directly. AB is 80. Wait, how?
Oh,
Oh, yeah. AB is 80.
that's nice.
Mhm.
Yes.
Is A Q the midpoint of DT? Like it looks true, but
Yeah.
sure.
It's actually good. I never noticed it, OT.
But how do you even use this?
I don't know, like, it just seems like a good point.
Yeah. Like I was thinking if you construct a point X such that angle QCX is Y.
QCX
Like
is
point X on QT.
QT. I see. I see. I
Yes.
see.
Then
So,
like D and X are symmetric about Q, right?
yep.
And then
I get it.
maybe you can focus on like triangles DAQ and QXC.
I
But
get
I'm
it.
not sure how that will work out.
X and QT such that?
Like
Uh, QCX is equals to Y.
something like
Oh, then you'll get
Okay.
AD is also equals to AX. Oh, that is basically just reflecting D over Q, right?
yes. No.
Yeah.
No, right? You want DQC, right?
What?
You want DXC, right? To be Y. No.
No.
No, no, sorry.
QCX.
Yeah.
QCX.
QCX.
So DXC, right? Where this angle.
No.
Then,
The angle at C in triangle QCX.
oh, I'm stupid. That's, yeah, that is reflecting, yes.
Yeah. Okay. That won't be helpful, I guess then.
But T was nice.
Yeah.
T was a nice point. Anyways, I'll just give a hint. We haven't used PD is equal to PB yet. Like, we have used the angle thingy, but
Oh, PD is tangent to
yes,
triangle DSE.
yes. Are we done?
No, I don't think so.
Okay.
Oh, that PDA is also Y, right?
Yes.
So Y minus X will be equals to,
So we want this angle, right?
yeah, okay, we are done.
Just want this angle.
Oh, you can just use that exterior angle property, no?
Yep.
X plus B is Y plus 2C.
Yep. So you have that angle PDB is 2C and DQP is B. So this angle is 2C minus B. And we are done. So is there any questions? I'll just like summarize the solution once. So first, we had that angle. Okay, just see the diagram. Right here. So first we saw that angle ABQ is equal to angle ACP, giving that AB was tangent to circumcircle of PQC. And basically we got similarity that ABQ is similar to what ACB. From this we got that angle BQA is equal to B, and so DQCR is cyclic. And then we proved that PB is also tangent to circumcircle. So PB square, which is PD square, is equal to PA times PC. So from this we get that PD is also tangent to circumcircle of ADC. And now we just angle changed. To prove QB is QR, we just just bash angle chasing. Basically defined QRD as Y and CBR as X, just for like simplicity. And we got that CAR is X and DCQ is Y because DQCR is cyclic. And then because of this relation, we had that PD is also tangent to the circumcircle of ADC. So PD is also Y. And then basically we had. So the main part of the problem, like power of point and angle chasing were good together. This problem wasn't super hard, but all I wanted, the reason I did this problem was basically to show that power of point and angle chasing actually work well. So, are there any questions with the problem?
No.
Okay. So, perfect. Now, let's go to an actually very hard problem, which just uses angle chasing, but it's like brilliant problem. So,
Very brilliant.
yeah, just legendary problem.
Does anyone know the source? I'm curious.
Yeah, I am also very curious. Do people know the source of this problem? Or has anybody done it before? I just try to draw diagram. Like I'll be probably using GeoGebra for this. Okay, good, nobody's done it. It's so hard to draw diagrams. Oh, oops, I should actually show the problem as well. Yep, much better. It changed color because of it's not a straight line. It's just 1 second draw diagram. X, Y. So X, Y, Z is the triangle determined by the lines LA, LB, LC, and hopefully it's tangent in this. Oops. Not tangent. Perfect. So we want to, so we are given any line tangent to circumcircle of ABC, and then we reflected that line across BC, AC, and AB. And let's say the triangle it determines is XYZ, and we want to prove that the circumcircle of XY is tangent to the circumcircle of ABC. So like take till 740 to just get a feel of the problem. And if you want more time, have more time. This is very hard. So like I do not expect you to come up with solution at all, and if you can, you're brilliant. But just give any idea that you come up, like any nice angles or any good nice points that you want to add, or basically some nice concurrence, collinearity, anything that you just come up with it, just say it. It's because this problem is quite involved. Just I like wait for 5 minutes. And if you people want more time, I'll wait for longer. Perfect. So just get a feel of the problem. Okay, so any ideas for the people one more time? Hello, people. Hello, people. Am I audible?
Yeah, you're audible.
Oh, what do we do, bro?
No, what do you want to do?
I don't know. Can people hear?
Yes.
Okay. Do you want to try the problem for more time, or do you want a hint? Hello, people. Okay, anyways, so I'll just give a hint. So basically, just go back to the OMC one, the mirror whiteboard. Uh, uh, uh. So basically, like these points are quite nice. Try to do some like stuff because basically you're reflecting lines, so you don't have much of an information other than angles. So all we'll be doing in this problem is angle chasing, and reflecting lines means this angle is these two angles are equal. Basically, AB bisects YX and the original line L. So we have a lot of like angle bisectors. Does that help? I'm sorry, were you saying something? Like we couldn't hear. Like, can you like voice is quite low.
Sorry, I just need to spit out food.
Yeah. So we couldn't get what you were saying. Okay, I'll give like a hint. You have AF bisects the external angle YFE, and AC also bisects the angle ZEF. So in triangle XFE, you have that AF is an external angle bisector and AE is also an external angle bisector. So you must have that AF. So you must have that AX also bisects angle FXE or angle YXZ. So if that AX is the angle bisector of YXZ, and so BY must also bisect this angle, and so must CZ. So basically they must, oops, that line. Basically BY and CZ must concur at a point, which is like the incenter of the triangle XYZ. Is this clear?
Yes.
Perfect. So like it looks like the incenter is like quite close in the circumcircle of ABC. And like just because this is a very bad diagram, it doesn't look precisely. Like if you're in a contest, you maybe have a better diagram, and it may be like it may be easier to spot the tie lies in the circumcircle. So is it true that tie lies in the circumcircle of ABC? So just do angle chasing. Basically, you have that A was the excenter of triangle XFE. So angle FAE, oops, FAE is equal to 90 minus angle FXE by 2. And angle YIZ is equal to 90 plus angle YXZ by 2. So like adding these two angles, just because FXE is YXZ, you have that FAE plus YIZ is equal to 180. But note that angle FAE is equal to angle BAC and angle YIZ is equal to angle BIC. Basically, this is BIC and this is equal to angle BAC. So you just add these two angles, you have that they sum to 180. So BAC plus BIC is equal to 180. So you have that I lies on circumcircle of ABC. So I'll do it on the GeoGebra to just make sure. So you can see that AX, BY, CZ just conquer at a point. Which is also on the circumcircle. Now they just probably explores more stuff. Like maybe add a few more points which are helpful, some nicer angles you can see. Just try.
Can you go to the GeoGebra diagram once?
Okay, sure. I was talking when I was muted. Yes.
Take okay, the labelings. Uh,
Oh yeah. I'll just do this thing. Yes.
no, can you just hide this lines AX, BY, CZ, like the lines?
Sure. Yeah.
And take this. One second.
Right pointer.
Take a random point on YZ.
Oops, 1 second. Oh, sure.
Show the point I. Like, do not hide that.
Okay.
The point.
Yeah.
Consider the circle YDI.
YDI. Circle. Y.
Yeah, circle through three.
I.
And ZDI.
Z. D.
They're not concurrent. This should be as far as I know.
How can you do it with any random point?
No, it was true.
This, no, see, I just gave it a shoot. Ding. It passes now. It also passes now.
No, this also doesn't pass.
See, this does now, upper wala circle.
But not the below one. Both should pass.
ऐसे हो सकता है,
I
both
think
ऐसे
I
हो सकता है.
consider the circle.
भाई ZI, ZDI and YDI का तो D और I ही common points होंगे ना. D कैसे आ सकता है?
Oh, right.
Genius.
No, I think I had a different name than I forgot. I don't remember it.
Sad. It's a legendary problem. Okay, do people have any idea? Good morning. Hello, people. Do you have any idea? Sad. Okay, fine. I'll just give another step. So, like, this was natural, I guess. Basically, just because you're reflecting L and P is a good point on L, why not just reflect P? Like, just reflect P over PC to be, say, PA. Reflect P over AB to be PC. And reflect P over AC to be PB. I'll erase this part. So like by that Simpson thing, PA, PB, PC are collinear. So they're not like bad points. And now I'll just give it away just because I don't have any time. There's half an hour left. What is angle PA, BPC? Also before that, notice that the angles of XYZ are really good. Recall that we had A seccenter of XFE. So angle FXE, or no, sorry, angle FAE is equal to 90 minus angle FXE by T. So you have that angle FXE is equal to 180 minus 2, which is really good and awesome just because P was any arbitrary point and XYZ are quite variable. So you have that the angles X, Y, and Z are quite nice. What is angle PA, BPC? Okay, so I see more people joining. Okay, this is the problem that we are trying. Like if ABC is a triangle and L be a tangent line to circumcircle of ABC, now you reflect the line L over BC, AC, and AB. So the intersection of these lines forms a triangle X, Y, and Z. You want to prove that the circumcircle of X, Y, Z is tangent to ABC. So now we first see that like define D as the intersection of L and BC, E as the intersection of L and AC, F as the intersection of L and AB. We have that BC bisects the line L and LA. LA is like the reflection here. And so we have that AF and AE are external angle bisectors of XFE and XEF. So A is eccentric of XFE, and so AX must bisect angle YXZ. Similarly, BY and CZ. So basically, AX, BY, and CZ conquer at some point I. And then we also prove that I lies in circumcircle of AB. And PA, PB, PC are reflections of P across BC, AC, and AP respectively.
By the way, in the GeoGebra diagram,
Uh,
can you do this? Okay, it's loading.
Yes.
Like take a random point when it loads. Take a random point on YZ.
Okay. Then
Draw the circle YTD and ZTD.
ITD and ZTD. YDP and ZDP. Sure.
Okay, why is this not nice? I remember this being nice.
This is not nice. Like you can't have it with random point, right? P must be a good point.
No, there was something with the random point
P
also.
very good.
I think I'm taking the circles wrong because like T and D are the two intersections only, no?
T and
D already make up the two intersections.
exactly. If you take YBD and ZCD,
Yeah, maybe try that.
I really doubt one second. I'll delete these circles.
Just undo it or delete fine.
I've done a lot of movement, right? And also takes movement into.
Yeah. You can just click it instead of swiping.
Right. Uh-huh. This YBDY and CDZ.
Yes.
Circumference.
Yes. Yes, this was the clip.
Interesting. 1 second. This should not be hard though.
Yeah, this is a angle chase.
Yeah, of course. Entire problem is angle chasing.
Yeah.
Yeah, okay, fine. I'm done with angle chasing too, right?
Yeah.
Okay, so yeah. So that was a nice claim. Basically, okay, fine. Let's just prove that claim only. It'll be good. So for any point D, the circumcircles of YBD and CZD conquer at the circumcircle of ABC. Oops. Why is this true? Just because let this point say be amount of points. U, we have angle PUD. This is equal to angle BYD, which is equal to 90 minus B, and angle DUC is equal to angle DZC, which is equal to 90 minus C. So when we add these two angles, we get BUC is equal to angle A. So U lies in circumcircle. So awesome. That was a nice claim, lady. Let's just delete all this stuff. Now let's go back. And again, I don't have time. We'll just give away this claim. So you have PA, PB, PC. Now, like PA, PC are not good, so we'll try to like use reflections and throw this angle that one vertex is P. So we can write this as PCBA plus angle PABA, which is equal to angle PBA and PABA. We can write this as like 180 P minus angle PABP, which is equal to angle PBA plus P minus, oops, this should be like A, angle PBC. And angle PBA minus angle PBC, this is equal to B. So this angle is 2, which is nice. And so we have angle PABPC is 2B. And this angle, remember this was 180 minus 2B. So we have that Y, PC, P and P are concyclic. So oops. Basically this circle. So this is quite good, and this circle actually looks like it passes through T. And so just because T is quite symmetric, we must have this true for everything. That is X, P, C, B, and A must also be cyclic. And like we don't know it passes through T, but it just looks like. So if we just try to draw another of these, it almost does seem that it passes through T. Just because this diagram is very bad, and if you probably at a more accurate diagram, this may be slightly easier to spot. So we have that, we just hide these two circles. I'll also hide point T. First, I'll just deflect P across this. Oops. P across AB, P across AC, and label them slightly better so easier to follow. PA, PC and EB. And if we draw the circumcircle, y, p, c, b, p, a, it does pass through the tangency point. And so to prove this, like this gives 5 circles to be concurrent, which is just magic. So like this the first circle, that is y, p, c, p, p, a to be the first circle, x, p, c, a, p, b second, and the other z, p, c, p, a, p, b third. So basically we have like 5 circles which are concurrent, which is awesome. So we don't know it yet, we just want to prove it. So if we just define, say, the intersection of the first and second circle to be some point S, we want to prove that S lies in circumcircle of ABC. Can we do that? Yep, angle chase again. Basically, very similar to the proof we did before. We have that angle ASB, sorry, ASBC is equal to, not ASBC. We have angle BSBC is equal to angle BYBC, which is equal to 90 minus B, and angle ASBC is equal to angle AXBC, which is equal to 90 minus B. So the sum of these are two angles, which is equal to ASB is equal to C. So we have that C lies in circumcircle of ABC. Now the intersection of the first and second circle lies in circumcircle of ABC. So if I intersect like the third circle with, say, this first circle, that must also lie in circumcircle of ABC due to symmetry. But just because that is a unique point, the other point is B, and B does not pass through this circle because of the other intersections like C. That's just some stupid stuff. But we just prove, we can just use this proof again for the first, second, and third circle to prove that these 3 circles conquer at the circumcircle of ABC. So now we are like perfectly sure, like mostly sure that S must be the desired tangency point. But we still don't know. It's just because we still want to prove that S also lies in the circumcircle of XYZ, and that would be sufficient to perfectly know that S is the tangency point. And then we can just draw the tangent at S and do stuff, but we'll do that later. So first, we now want to prove that S lies in circumcircle of XYZ. Can we do that? I'll just try to take this diagram because it's much easier to write it. One second. 1 second. Let me just paste the diagram. If we will try to prove that. Zoom in a bit. Oops, don't zoom. Oh, what is happening? Why is this mirror does stuff like this? God. I'm extremely sorry for this poor moments. Okay, perfect. So we want to prove angle y s PC plus angle PC SX is equal to angle YZX. YSPC. That is correct. Yes, precisely. We want to prove this. So we have that angle YSPC is equal to angle YBPC and PCSX is equal to angle PCAX. We want to prove that this is equal to angle YZX, but remember that YZX is just basically 180 minus 2C. So now again, we'll just try to use the previous idea, that is try to remove P and PC. Yeah, try to remove P and PC so that we can just use reflection and make one vertex to be P. So let's start with YBPC. So we can write this as angle PCBA minus angle PCBA minus angle YBA, which can be written as angle PBA minus angle YBA. And angle PCAX, we can do some similar stuff. Like this thing is just equal to angle YBPC and angle PCAX is equal to I can write this as PCAB plus angle XAB. Now PCAB is equal to angle PAB and XAB is just XAB. Now if we add both of them, we get that we want to prove PBA, PBA minus angle ABA plus angle PAB plus angle XAB is equal to 180 minus 2C. So note that angle PBA and PAB is sum to 180 minus angle APB in this triangle, and APB is just C. So we can write this as like 180 minus C plus angle XAB minus angle YAB. Now XAB minus YAB, like basically XAB is this angle and YAB is this angle. The difference is just angle AIB, or the negative of AIB. Now, as I lies in circumcircle, so we have that AIB is angle C only. So we have that this is also equal to 180 minus 2C. So awesome. We finally have that S also lies in circumcircle of XYZ, and we are sure that S is the desired point of tangency. Are there any questions with this part?
No.
Perfect. Awesome. So now we hope to prove, like now we will prove that S, the tangent at S is basically tangent to both circles. Is the diagram again once? So now we just do the tangent at XYZ. Oops. Now we just draw the tangent at oops. Now we draw the tangent at XYZ. Sorry, the tangent at S to XYZ, and let like any point be say K. And we prove that this line is also tangent to circumcircle of APC. And so basically, just because this line is tangent to circumcircle of XYZ, we have that angle KSY is equal to angle YXS. And what is YXS? Just because angles with X are actually good in this circle, like the circle XPCAPB, and basically that's how we can eliminate X. So just try to write this angle as PCXS PCSX, which we can write as say 180 minus angle PCAB, sorry, PCAS. Now again we'll try to remove PC, which is equal to 180 minus angle PCAB minus angle BAS, which is equal to 180 minus angle BAB minus angle BAS. And so what do we want to prove? We want to prove that this line, the line KS, is also tangent to circumcircle of APC. And just because we started with like KSY, and Y has like good with B, like YB have some nice properties. So like we'll try proving that angle KSB is equal to angle BCS. So we want this. So basically, we want that angle KSY plus angle YSB is equal to angle BCS. And what is angle YSB? We can again write this angle as YSB. Right here, we can write this as this angle. We can write this as angle BPCX. So what do we want to prove? We want to prove angle 180 minus BAB minus angle BAS plus angle BPCX is equal to angle BCS. Okay, cool. How do we do that? Like, so S is like not good. Like first thing that we should do is just eliminate S, but that's super easy just because 180 minus angle BAS is equal to BCS. So we are just left to prove angle BPCX is equal to angle PAB. This is all we want to prove. And so let's see what we do. So we have angle BPCX is this blue angle, and we want to prove this is equal to, change color, this red angle. We want to prove that this blue angle is equal to this red angle. And that is quite easy, just because just notice, oops, by reflections, we had that AB, this point was F, we defined it earlier. So this blue angle is equal to this blue angle. But because FP is tangent to circumcircle of ABC, so the blue angle is equal to the red. So finally, after so long stuff, we proved a lot of claims and loads of angle chasing and nothing else other than angle chasing. We finally managed to finish the problem. Are there any questions with the problem or any part of the proof? What's the source of the problem? The source of the problem is 2011 P6. Yes, a P6 just and which is like it is hard. It's very hard. That's why it's a P6. And also in 2011 there were people who had a score of 007 in day 2.
007.
Yes,
What were they doing in the
I have
course?
no clue, but there were scores of 007 and just
Oh, maybe they were complex bashing this. There are a lot of complex bash solutions. Like it makes sense that it will take like long enough.
like complex bash is still not so natural either. It is still
For
lot of-
complex bashers, everything is natural in bash.
you still have to make a lot of claims. You just go bashing everything. Still.
Wait, did someone get 007 in the contest?
Yes.
Bond, James Bond.
Yes. And this was the P6, so imagine like why would you even try a P6 before doing the P4? People literally had
I mean, geomains are the weirdest creatures to be alive, so yeah.
oh like that's not so bad. Geomains are good. They're very intelligent. Like if you are even an anti-main or a combo main, you won't do 007.
Yeah, like 007 is greater than 770. I agree.
Yes. So geomains actually have like a too good at geo. Just too good at geo. Like Krishna. Legendary geomain. Okay, so are there any questions about any part of the proof? It's a really brilliant problem. So I'll just quickly summarize. Let the GeoGebra page load once. We first prove AX, BY, and CZ are angle bisectors of angle XYZ, triangle XYZ. And so AX, BY, CZ conquer at some point I. By the easy angle chasing, we can prove I lies in circumcircle of ABC. And then we reflected P across BC, AB, and PC to get points PA, PC, PB. And then we proved Y, PC, BP is cyclic, and Z, PA, CPB, and the other similarly are cyclic. And then by just a leap of faith, we thought that the required tangency point lies on the circumcircle of Y, PC, PPA, which turned out to be true. And the remaining part is just super angle chasing. Just long angle chasing, but just kind of do it. Right, that is true, Anurag. No, like, they're not bad. They're pro. Okay, fine. That's it from my side. Thanks for attending to those who attended.
Thanks for the class.